This is the fifth lecture from module 4. Here in this lecture we will be discussing the speed control methods of three-phase induction motor. In the previous lecture we discussed the stator voltage control. Now we will discuss the stator frequency control of induction motor. As we know, the synchronous speed of induction motor is equal to 120 F by P, where F is the supply frequency and P is the number of poles of the machine. This can be represented in radians per second as omega ms is equal to 4 pi F by P. So here omega ms, that is the synchronous speed, is directly proportional to supply frequency. That means synchronous speed of the induction motor can be controlled by controlling the supply frequency. That means its rotor speed is also possible to control using the supply frequency control. By varying the supply frequency, you can control the speed of an induction motor. Now let's see what will happen if you control the speed of an induction motor by controlling the supply frequency. Here this is the per phase equivalent circuit of the induction motor that we have already familiarized in the first lecture. Here V is the stator input voltage, Rs and Xs are the stator winding parameters, E is the stator induced EMF. So the stator induced EMF, that is the voltage induced in the stator, is directly proportional to the supply frequency and the air gap flux. The supply frequency and the air gap flux. Now for simplicity, we are going to neglect the stator drop. So by neglecting the stator drop, the motor terminal voltage, that is V, becomes equal to E, because we have neglected the drop in this impedance. So V equal to E. So we can say V is proportional to phi F. Okay. So keep in mind we have to vary the value of frequency in order to control the speed of the motor. So consider the equation. Here we are keeping supply voltage as constant. We are only varying the supply frequency. Then if you reduce the frequency by keeping supply voltage constant, then obviously the flux will increase, air gap flux will increase. So the induction motors are normally designed to operate at the rated value of flux, and that rated flux will be very near to its magnetic saturation. That means if you increase the flux above the rated value, then the machine will go to magnetic saturation. That means if you are supplying the machine with a rated voltage, and if you are in reducing the frequency below the rated value, then the magnetic air gap flux will go above the rated value, which will lead the machine to magnetic saturation. So if the machine saturates, then this will increase the magnetizing current, distort the line current and voltage, and increase the core loss and stator copper loss. So these are not at all desirable thing. So we have to avoid this situation. Let's consider one more possibility, that is if you are increasing the flux in order to increase the speed of the machine above the rated value. If you increase the frequency above rated value, keeping voltage as constant, then the flux will reduce below the rated value. If the flux reduces below the rated value, then the torque capability of the machine will reduce. So this is also a drawback. So these are the two possibilities of stator frequency control. Now let's see what is the solution for the first problem, that is magnetic saturation. In order to avoid magnetic saturation, we have to keep the flux constant. In order to keep flux constant, we have to ensure that the ratio V divided by F should be constant. If phi is constant, then V by F should be constant. V by F should be constant means if you are increasing the frequency, voltage should be increased along with that. And similarly, if you are reducing the frequency, then voltage should reduce below, reduce along with that. So that is the solution. The variable frequency control below rated frequency is carried out by reducing the stator voltage V along with the frequency F so that the flux is maintained constant. But this cannot be done above rated frequency control. That means if you are increasing the frequency above rated value, then you have to increase the voltage above rated voltage. This cannot be allowed. So above rated frequency, the motor is operated at constant voltage because of the limitation imposed by the stator insulation or by supply voltage limitations. So if we can increase the frequency up to rated frequency, and we can increase the voltage along with that up to rated voltage. So above rated frequency operation, we have to keep supply voltage constant. So keeping supply voltage constant, we will increase the supply frequency in order to run the machine above rated value. Then the flux will obviously decrease, thereby reducing the maximum torque capability of the machine.